So indeed, we're about to discover that if you double the ramps, do you indeed double the fun? Of course you do. You also double the work, but that's where the fun comes in. So if I do this sort of thing, a 5 kilogram block and a 2 kilogram block tied together, the 2 kilogram is on a 70-degree angle, the 5 kilogram is on a 25-degree angle. Which one's going to win? And normally you would assume the heavier one does, but because it's on a steeper angle, less of its gravity is being used to slide. And this one is on a steeper angle, so more of its gravity is trying to make it slide. So you can't really see, it's not intuitively obvious anyway, which one's going to win. So we have to do the math. For this first one, I'm going to leave friction out of it so that it's not too complicated. I'm also going to give these some names so that I don't have to keep calling it the 5 and the 2. This can be Bill, and this can be Tina. Why not? So for Bill, I can do a force of gravity for Bill, and I can do a force of gravity for Tina. So Tina's will be 2 times 9.8. That is 19.6. And Bill's will be 5 times 9.8, and that's 49. Now Bill's gravity and Tina's gravity, because they're both on ramps this time, is going to have to be split into a piece that's parallel and a piece that's perpendicular. So for Bill, the parallel part will be the full gravity multiplied by sine of 25. I'm going to get an approximate for that. And the perpendicular part will be the full gravity multiplied by the cosine, 25. And for Tina, the parallel part will be the full gravity multiplied by sine of 70. And the perp part will be the full gravity times the cosine of 70. So I get some approximate values in there. Let's see. 49 sine 25 is 20.708. $49 cos 25 is 44.409. $19.6 sine 70 is 18.418. And 19.6 cos 70 is 6.704. Okay. So, just like in the last examples where there was a single single thing on a ramp and we had this friction involved and all that other stuff, we did have normal forces pointing straight out of the blocks, and those happen to match the perpendicular forces. So I can acknowledge that, no problem. And then I can try and do a net force. So I have to go through and I have to look at all these things and I have to try and find the biggest number. So I have a 49 there, 19.6, 18, 20, 44, that's almost but not quite, and that's not. So there it is. There's our winner. That's Bill's gravity. But we can't use Bill's gravity because this isn't aligned onto our surfaces, so that one's out. We gotta hunt for another one. 44.09, fine, but that is the perpendicular component. That's not actually sliding along our ramps. So that's a perpendicular component. So I'm looking between these two. There it is. This one's bigger. So Bill's tendency to slide is 20.708 newtons. And Tina's tendency to slide is 18.418 newtons. That means that Bill's going to win. So using that information, we could do a net force and we could get the net acceleration. F net would be 20.708 subtract 18.418, and that should give us our net mass, net acceleration. So 20.708 subtract 18.418 gives me 2.29. Their net mass is 7 kilograms. So 2.29 divided by 7 gives me my net acceleration. Which gives me 0.327 meters per second squared. All right. So we've got everything we need to know about this particular system. We could do the tension and the strain, but I'm just going to skip that because I think really the issue here is how to break forces into components and then how to compare them. So now that we have this one done, I'm going to clear it off and then we'll try one that has friction involved. Okay, so here we have, let's say, Kim and Roger hanging out on this triangle-shaped thing. Just for fun, we're going to give Kim a certain type of material. So Kim's maybe made of copper and Roger's maybe made of iron. I'm not sure exactly what they are. But the fact that they're different materials has resulted in a slightly different coefficient of static friction between those two blocks. Both of them are on ramps, so I'm going to have to break their gravity into more convenient reference frames. So I'm going to start with the gravity calculation for each. FG, you maybe notice that this is always the first step. Get gravity because it's pretty straightforward. So on Kim's side, it would be 20 times 9.8. That's 196. Newtons. And on Roger's side, it would be 12 times 9.8, which gives me 117.6. Alright. So if I break those into perpendicular and parallel components, the parallel side for Kim will be the full gravity and then the sine of 60. Get an approximate value there. The parallel on Roger's side will be the full gravity sine 25. Get an approximate value. The perpendicular part will be full gravity cosine 60. Gravity cosine 25 on Roger's side, get approximate values there. So 196 cos 60 gives us 98. Oop, that should be sine 60. 196 sine 60 is 169.741. 196 cos 60 gives me 98. 117.6 multiplied by sine 25 gives me 49.6999, which I will round to 49.7. And 117.6 times cosine of 25 gives me 106.582. All right. Whew. So there's friction involved, so I need to identify the normal force first, because the friction depends not only on the coefficient of friction, but how hard those pieces are pressed into each other. So my normal forces are the perpendicular components. So the normal force acting on Kim will be 98 newtons. and the normal force acting on Roger will be this 106.582. So the force of friction acting on Kim will be the coefficient of friction on Kim's side, 0.4, multiplied by 98. We'll get an approximate for that. Force of friction on Roger's side will be the coefficient of friction Roger experiences multiplied by how hard he's being pressed into the block. Get an approximate on that. 6.582 times 0.6 is 63.949. And 0.4 times 98 gives me 39.2. Alright. So short of the tension in the string, that's all the forces involved in this particular system. Now I'm going to think a little bit about how this is going to work. Either Kim's tendency to slide down the ramp is going to drag Roger along and defeat all of these frictions, or Roger's tendency to slide down the ramp is going to pull Kim up the ramp and defeat all these frictions, or neither of them are going to be large enough to beat the other and the friction. I'm not sure yet. I'll have to actually plunk the numbers in and look. But what that means is the driving forces are either this one or this one, these parallel components of the gravity. Because without them, there's nothing actually driving the motion to work. And between the two of them, clearly, Kim's tendency to slide down the ramp is larger than Roger's. So if it moves, it has to move in Kim's direction. So when I set up my net force then, F net, I'm going to start with Kim's tendency to slide. That's 169.741 newtons. Now, from that, I'm going to have to subtract Roger's resistance. That's 49.7 newtons. I'm also going to have to subtract Kim's own friction. And I'm going to have to subtract Roger's own friction. So in order for this to move, this tendency to slide not only has to be able to stop Roger from sliding, but it also has to beat both of their frictions. So I'm not sure if that's going to be quite big enough yet. We'll have to actually add them up. So 169.741, subtract 49.7, subtract 39.2, subtract 63.949 gives me 16.892. So, in order for this system to move in Kim's direction, Kim's force had to be enough to beat Roger's tendency to slide, Kim's friction, and Roger's friction. And when I did this subtraction, I got a number left. So that means there's some left over. Almost 17 newtons are left over to start accelerating these blocks, which means the system will go. Once you have a net force, that's always net mass acceleration net, so pop that in there. Net mass between them would be 20 and 12 is 32 kilograms. So 16.892 out of 32 gives you the net acceleration. So these blocks, or the system, I suppose, the whole system will start to accelerate at 0.528 meters per second squared. So I mean, it's twice as much work because there are twice as many ramps, but it's not particularly complicated, right? The theme for this topic is that if you have gravity aligned in an inconvenient direction, you just split it up into components that are convenient, and then you start comparing them that way. So I'm going to erase this, and we're going to try one more just so we have a full set. So let's see. Let's talk about Edna and Tim. Okay, so launching into the process as we have every single time, I'm going to start with gravity for Edna, which would be 7 times 9.8, and gravity for Tim, which is going to be 5 times 9.8. That's 49. 63 and 56. 68 point something. 68.6. Okay. And we're going to have to break it up into components that are parallel to the ramp and perpendicular to the ramp. So parallel will be the full gravity sine 35. Full gravity sine 50. Get approximates on those. Then perpendicular force would be full gravity cosine 35. Full gravity cosine of 50. Get approximates on those. So 68.6 times the sine of 35 is 39.347. 68.6 times the cos of 35 is 59.194, or 56.194, sorry. (49 sine 50). 49 sine 50. 37.536. 49 cosine 50 is 31.497. All right. And just like in all the other examples, to do the force of friction, I need to know the normal force, and the normal force happens to be balanced by the perpendicular one, so that's how big the normal force is. Which lets me do my friction force. On this side for Edna, it would be Edna's coefficient, 0.1 times 56.194, which gives me 5.619 if I round to 3 decimal points. And on this side, I end up with Tim's coefficient of friction, 0.2 multiplied by 31.497, which is 6.298. If I round to 3 digits. Just going to check that one. Years of experience have taught me not to trust my brain. 6.2. 299, yep. See? Don't trust your brain. Okay, so net force calculation then. I'm going to have to look at this mess, and I'm going to have to decide whose tendency to slide is the biggest. So that's between this number and this number. And it looks like Edna's is the larger. So Edna's tendency to slide, 39.347, is going to have to beat Tim's tendency to slide at 37.536. And it's going to have to beat Edna's gravity. And it's going to have to beat Tim's gravity at 6.299. Now, I'm not going to bother putting this in the calculator, because if you just look at it, this minus this is about 2. 2 minus 5 is negative 3, and negative 3 minus 6 is negative 9. I have dropped into the negatives, so this is less than 0, which means there was not enough slide from Edna. Okay, so 2 reasons that might have happened. One, we screwed up the setup here, and it is in fact Tim that's going to win. So if I were to reverse those, put 37 here and 39 there, 37 minus 39 is negative 2. We've already lost. Negative 2 minus 5 is negative 7, minus 6 is negative 13. So even if I switch the directions, I still don't have enough slide. So there's not enough slide from Edna or Tim. And in that case, if neither block has sufficient slide to overcome all of the forces involved, then the system must be stuck. And it will just sit there until something else happens. Perhaps a bird will come and land on Edna's head, and adding the extra mass causes the system to start sliding. I don't know. But until something like that happens, there's an insufficient force imbalance to cause these things to move because the friction has held them too tightly. So there's a bunch of problems in the problem set for you to try where you have to split the thing into 2 different ramps and do friction on both sides. So good luck working on those.